Okay, so this was the expression up here that we wrote down for the time difference of the light traveling in the two different arms of the Michelson-Morley interferometer. Now we can simplify this expression using a Taylor expansion. Remember, a Taylor expansion takes this form. So if x is much less than 1, then the expression 1 plus x to the n is approximately, to first order in x, 1 plus nx. Okay, so we can use this. So for beta much less than 1, and we expect beta to be much less than 1 because it's this ratio, and we certainly know that the velocity of light is about 3 times 10 to the 8th meters per second. The velocity of Earth around the sun is 30 kilometers per second, so it can't be, so that ratio is indeed very small. Okay, and so what we would get is that 1 minus beta squared to the minus 1. So this term here becomes 1 plus beta squared. Okay, and the second term, which we can rewrite as 1 minus beta squared to the minus 1/2, is equal to 1 plus 1/2 beta squared. Okay, that's just using that Taylor expansion. So when you insert those expressions, those Taylor expansions for those two terms, then what you get is that the time difference, the two arms of the interferometer, is equal to 1 plus beta squared for the first term, minus 1 minus 1/2 beta squared for the second term, which when you simplify is just the length of one arm of the interferometer divided by the speed of light in the rest frame of the ether times beta squared. Now let's check to see whether this expression has the right dimensions. Beta is dimensionless because it's the ratio of two velocities, so this has no dimensions. L has dimensions of length. C has dimensions of length per time, and so indeed this total expression has units of time as we expect. The Michelson-Morley experiment was a really beautiful experiment, and one of the cool things about it is that the whole apparatus, this whole interferometer, is floating on a bed of mercury. Okay, this whole thing here, this whole interferometer was floating on a bed of mercury. And so what they did was that they measured this time difference delta t, okay, and they then rotated the interferometer by 90 degrees so that TA went to TB and TB went to TA, and then they compared those two things, and so the time delay between the arms will change by 2 delta t, okay, when they do that. And that gives them a little bit more precision because they basically have effectively increased they've increased the time delay by a factor of 2 that they can measure, so that increases their precision by a factor of 2. Remember that delta t is measured by observing a shift in the interference fringes of the recombined light waves at the detector when they get recombined using the beam splitter. And also, as we said before, when delta t equals 0, the interference pattern is centered at the detector, but when delta t is not 0, it shifts. So they calibrated their instrument, and they found that for delta t equals the period of the light wave divided by 2, the fringes shift by that same ratio, 1/2 of the spacing between the fringes. So if this is sort of an interference pattern over here, okay, and this is the spacing as indicated in green, then when delta t is equal to half a period, then the interference fringes would shift also by half space.